All right, let's start chapter 3, exponential and logarithmic functions. We'll do exponential functions today, and we'll do logarithmic functions on Monday and Tuesday. We'll combine them both on Thursday and Friday of next week, and then we'll talk about what happens the following week, the week of Christmas vacation. So let's start with exponential functions. The thing I want you to remember here about exponential functions is if we take a number like 5 and we raise it to successively larger powers. So we go 5 squared, I get 25. 5 cubed, I get 125. 5 to the fourth, I get 625, and so on and so forth. So numbers greater than 1, if you raise them to larger and larger powers, it's going to get very, very large. Whereas if you take a number like 1/2 and you raise it to larger and larger powers, so 1/2 squared is actually 1/4. 1/2 cubed is 1/8. 1/2 to the fourth is 1/16. It's getting smaller and smaller and smaller. It actually approaches 0. Okay, so again, numbers larger than 1 get really big. Numbers smaller than 1, but still positive, get closer to 0. So try to keep that in mind as we go through this. So the definition of an exponential function. So we start with the exponential function f with base b is denoted by f of x equals a times b to the x, where b is positive. Okay, that's what anything greater than 0 means. And it does not equal 1. We'll talk about that in just a second. And a and x are any real numbers. So what you have here, so as an example, you'd have f of x equals maybe 3 times 5 to the x power. So again, the thing here is this. This is the first time we've seen functions where the exponent is changing and the base is going to be fixed. This number is significant because this is the y-intercept, barring any sort of transformations. And we see that because if I put 0 in here, anything to the 0 power would be 1, and 1 times 3 would be 3. So that's the starting value in a lot of these problems where we're looking at applications of exponential and logarithmic functions. Okay? So why can't it be 1? Well, it says note the definition of the exponential function, the base b equals 1 is excluded because it would yield 1 to the x power, and 1 to any power is just 1, which would turn the entire function not into an exponential, but just be a constant function. All right. Before we go further, let's just talk about rules of exponents. This here on the left, we have just the definition of what it means to raise something to a power, okay, which you should know. Key thing right here, anything to the 0 power is 1. A lot of students think it's 0 or something like that. It's not, it is 1. Another key one here is if I raise something to a negative exponent, all it does is reciprocate things. And we'll see that down here in this one here in just a moment. But x to the negative 1 is 1 over x. It does not make anything negative. So please do not make that mistake. A product of powers, we add the exponents. A power of powers, we multiply the exponents. Okay, over here is the one underneath that. If I raise x to the negative m power, I get the reciprocal of x to the m power. I could also write it by putting 1 over x in parentheses and raising it to the m power. Down here, if I have a product of powers raised to a power, that power is multiplied by each of those powers inside. It's similar, it should look similar to like a distributive property, but it's not. And here we have a quotient of powers where we subtract the exponents. If we have a quotient to a power, that power, just as under multiplication over here, that power gets given to both of the pieces of the quotient. Another one, fractional exponents. X to the 1/2 power is the square root of x. And x to the m over n power, the n here tells you what root you're taking, and the m is what the normal power is, the exponent. So if I said x to the 7/3, this would be the cube root of x to the 7th power. So let's take a look at just a generic exponential function. Notice here, I left off the a. Really what I'm doing here is I'm just telling you that a is 1. Okay. And so let's take a look at this. If b is greater than 1, so this is a function like 2 to the x, 5 to the x, something larger than 1, the domain, Okay? Well, take a look at it. If I take, for example, a function f of x equals 2 to the x, I can raise 2 to absolutely any power that I want to. Positive powers, negative powers, zero, fractions, decimals, whatever. So the domain of a function like this is all real numbers. However, if I raise 2 to any of those powers, I will never be able to get 0 out, nor will I ever be able to get a negative number out. I will, on the other hand, be able to get out any positive number whatsoever. So the range is all positive real numbers, which we denote by the interval 0 to infinity. Since I'll never get 0 out, there's never going to be an x-intercept. Again, barring any sort of transformation where we shift the graph up or down. The y-intercept is 0, 1, again, because if you plug in 0, anything to the 0 power is 1. Horizontal asymptote. Go back to what I was talking about before. Similar, we'll tie that together afterwards, but if I raise 2 to the 0 power, I get 1. If I raise 2 to the negative 1 power, using the rule up above, that's the reciprocal of 1 over 2, or 1/2, the reciprocal of 2. 2 to the negative 2 is 1 over, it's the reciprocal of 2 squared, so it's 1 over 4. 2 to the negative 3 is 1/8, and so on and so on. So as x goes to negative infinity, the function is going to 0. So that's what this statement says here. As x goes to negative infinity, the function approaches 0. And we can see that in the graph over here, that as I move towards the left, that function is getting smaller and smaller and smaller. Okay? Notice the function is increasing over the entire domain. It is always going to go up. We call that exponential growth, and it's continuous. There's no breaks. There's no, any sort of problems with the graph. All right. If you take b and make it between 0 and 1, so now you're dealing with a function like, and this is this one here, 1/2 to the x. Same deal. All real numbers is the domain. You can raise 1/2 to any power you want to. And the reason really is this. This is going to tie together the rules of exponents that I mentioned up top in the graph we just did. 1/2 to the x. I can write any fraction as the reciprocal of a number greater than 1. So 1 over 2, I can rewrite as 2 to the negative 1 to the x. And then because I have a power to a power, this is 2 to the negative x. And then using the rules of transformations, this is the graph of 2 to the x, which we just looked at, reflected over the y-axis. And you should be able to see this. If we scroll back, you should be able to see that this graph is the other one reflected. So our domain is all reals. The range is still going to be all positive numbers. It'll still never hit the x-axis. The y-intercept is still 1. Now, instead of as x approaches negative infinity, the function approaches 0. Now it's as x approaches positive infinity, the function gets closer to 0. So it's still the x-axis or the line y equals 0 that is going to be the horizontal asymptote. This function's decreasing. It's called exponential decay, and it's continuous. So in the next videos, we're going to go ahead and take a look at some of these examples.